Okay, so today we will solve some problems using Wester's approximation theorem. Okay, so we will start by solving an easy exercise. So, okay, problem one is show that so sorry. Let A belongs to R plus. So by R plus we mean this set of a positive real number, a positive real number, so that there exists a sequence of polynomials so that n converges to mod x uniformly on this interval and En of 0 equal to 0. So value of this polynomial En at the point 0 equal to 0, this is for all n. Mhm. So proof. So we will solve this problem using Wester's approximation theorem. So see that so take f of x equal to mod x. First fix a and define and define f of x equal to mod x where x belongs to minus a to a. So clearly f is continuous function. F is continuous function on this interval. Now by Wester's approximation theorem, we can say that there exists so now by Wester's approximation theorem, we get that there exists a sequence of polynomial ignited also. So there is a sequence of polynomial, sequence of polynomial, say Pn, such that we take this is Qn, such that Qn tends to F uniformly on this. Now define Pnx equal to Qnx minus Qn0. So see that since Qnx converges to mod x, so Qn0 converges to 0 as n tends to infinity. So see that Pn of 0 equal to 0 for all n, and Pnx converges to fx, because Qn0 converges to 0 as n tends to infinity. Okay, and Qnx converges to mod x. Okay, so check that Pnx converges to f uniformly on minus a to y. Okay, clear? Okay. So exercise, okay, write it as homework 1. So that there does not exist any sequence of polynomials which converges uniformly from mod x on R. So there does not exist any sequence of polynomial which converges uniformly on uniformly to mod x on whole real line. Yeah, we see. Hey, yes. Okay, so problem two, from the previous this class, I gave an exercise so that if 0, 1 to 1 x to the power n f of x dx equal to 0 for all n belongs to n union 0, then f equal to 0. Provided, so what is f? What was f? So f is from 0, 1 to r continuous function. Okay. Solution. See that 0 to 1 x to the power n f of x dx equal to 0. This is one. And since f 0, 1 to r is continuous function, then there exists a sequence of polynomial Pn such that Pn converges to f uniformly on 0, 1. This is why Wester's approximation theorem. Now see that 1 implies so 1 implies this is an 1 implies integration Pnf equal to 0, 0 to 1 for all polynomial Pn. Why? So suppose Pn is a polynomial of degree n. So Pn can be written as a0, a1x, dot, 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 a dx to the power d, dn. So suppose Pn is a polynomial degree dn. And by linearity of integration, we can write this integration Pnf equal to 0 to 1 n of f a1 xf adn x to the power dnf. And 1 implies, so 1 says that, so this is 1 is true for all n belongs to n union 0. that is 0 to 1 integration f0, 0 to 1 x fx0. So all of these integration,
Excuse me.
yes.
How does one implies the product of Pn and F is equals to zero?
Uh, I'm taking no. So what is 0 to 1 PNF? PNF.
Oh, no, I mean, one says that product of xn into f of x is zero,
Yes.
and from whereas to the
Oh,
approximation theorem, we know that there should be a polynomial converging to f.
yes.
So, shouldn't this be product of xn into Pn is equals to zero?
No, no, see that, see that. So suppose your Pn is a polynomial of degree Dn, right? Then
Okay.
what is P 0 to 1 integration PNF? So PNF is equal to this, right?
Yes.
A naught F, A1, XF, this. Now integrate from 0 to 1, both sides. So this is 0 to 1 F, A1, A0, A1, A2, N are constant, right? So this is 0
Yes.
to 1 XF, and these are all of these are 0.
Why?
What does it mean? What does it mean? X to the power n f equal to 0 for all n means
Okay.
integration 0 to
Okay.
1 f
Okay.
0
Okay. Got.
x f 0, right?
Yes. Now I got it.
Yes. So okay. So this integration is 0. Now say that since Pn converges to f uniformly, sorry again same problem. So Pn converges to f uniformly so that Pn into f also converges uniformly to f square. Sorry, एक minute. So Pn converges to f uniformly. So check that. Pnf converges to f square uniformly on 0 1. You need to check this. So now we have this is equal to 0, 0 to 1. Now take limit n tends to infinity, 0 to 1 Pnf. This is 0. This implies 0 to 1 limit n tends to infinity Pnf equal to 0. This is this. Why? Because this convergence is uniform. Pnf converges to f square is uniform. What does it mean? Now from here I can say that key f square equal to 0 identically. Is it okay? F square is see this implies f square is identically 0. In fact, f square is greater than or equal to 0. Now, if possible, assume f square of x naught is still greater than 0 for some x naught. So since f is a continuous function, f square is also continuous function. And we know that continuous function is of sign locally. Okay, if g is a continuous function such that g of x greater than 0 for some point, then g of x naught is still greater than 0 in a neighborhood of x naught, right? In a neighborhood of x naught. Then from here we can say that there exists delta greater than 0 such that f square x naught greater than 0 for all x belongs to x minus x naught less than delta. That is minus delta plus x naught less than x less than x naught plus delta. So in this neighborhood, this is greater than 0. So this implies integration x naught minus delta to x naught plus delta f square still greater than 0. This is a contradiction because we have integration a to sorry 0 to 1 f square is 0. We already have this property. This is a contradiction. So there does not exist any point such that f square is not greater than 0. So therefore, you can say that key f square identical is 0. That means f is identical. Okay. So now, right, this homework 2. So let fg 0 to 1 to c. Fg complex valued function. Okay. Continuous. Right, continuous function. And x to the power n 0 to 1 f equal to 0 to 1 x to the power n g for all n belongs to this. Then show that if we get to g is more 3, what is proof? There exists a continuous function f from 0 1 to r such that integration 0 to 1 x to the power n f equal to 0 for all n belongs to sorry, n union 0 minus 1 is set minus 1 and integration 0 to 1 x fx equal to 1. We need to check, does there exist a function f beside this word 0 to 1 integration 0 to 1 x to the power n fx 0 but x fx equal to 1 means two, now we'll solve problem G. So I gave this problem last day. So that there does not exist any sequence of polynomials n such that n converges to uh, n converges to f uniformly as f equal to sin x on R b f of x equal to e to the power x on R c f equal to 1 by x 101. So this problem are easy. Just prove this by contradiction. Solution. So for sin x, suppose this one is easy, so I'll prove B. I show that B. So similarly, you can show that this is also true. Uh, okay, so for B, suppose there exists a sequence of polynomial such that e to the power x uniformly on R. So then, by definition, for every epsilon greater than 0, there exists n naught belongs to n, like that. For all x belongs to R, Pn x minus e to the power x less than epsilon. So put n equal to n naught. So Pn naught x minus e to the power x less than epsilon. Write this as e to the power x minus Pn naught x less than epsilon. So this implies e to the power x is epsilon. And suppose let assume Pn naught is a polynomial of degree d. Okay, then divide both sides by x to the power d plus 1. So this is Pn naught by x to the power d plus 1 plus epsilon x to the power d plus 1. So see that right hand side, this side goes to 0 as x tends to infinity, and this side is unbounded, right? This side goes to 0, but this side is unbounded. So this is a contradiction. So for sin x, you can show that by contradiction, the a non-constant polynomial for a, you can show that a non-constant polynomial p is bounded, is for some on R, and this is not possible. Okay, so yeah, easy. And for C, that f of x equal to 1 by x, this is not uniform. This function is not uniform continuous on this interval. But a sequence of polynomial, if a sequence of polynomial converges to it uniformly, and Pn is uniformly continuous for all n in this interval, then f should be uniformly continuous, right? This is also not possible. But see that AB is true. True means for AB there exists a sequence of polynomial Pn such that Pn converges to sin x uniformly on any bounded subset of R. Okay, so check that. This is your mark 4. So that there exists a sequence of Pn such that Pn converges to F uniformly as F equal to sin x, B equal to d to the power x on any bounded subset of R. Okay, so there's this polynomial on any bounded subset. This converges to F uniformly. Okay. Note 4. This problem 3. Problem 4. We let F 0 1 to R a continuous function so that there is a sequence of polynomial Pn such that Pn converges to F uniformly on 0 1 and and okay, so not a sequence, just I should write E. Yes. So that there exists a polynomial P such that such that before sorry such that so one if for every epsilon greater than 0 there exists a for every epsilon greater than 0 supremum over 0 1 px minus fx less than epsilon. So this is true. We can say that there exists a polynomial which satisfies this by Wester's theorem, Wester's approximation theorem. Such a polynomial exists. But say that with p of 0 equal to f of 0 and p dash 0 derivative of that polynomial equal to 0. So 1 is true by Wester's approximation theorem. You need to check this solution. So since if it's continuous, by Oyster's approximation theorem, Oyster's approximation theorem, there exists a polynomial E. Right, this is as Q. There exists a polynomial Q such that supremum of Qx minus Fx less than epsilon by 2. Okay, first take epsilon greater than 0 be an arbitrary positive real number. And since f is continuous function on 0, 1, we can say that such a polynomial Q exists. Now, define. Okay, so one thing is, sorry. So, see, if is continuous, then we can say that what? Uh, sorry. We can say that f of root x, this is composition of two continuous function, is also continuous function, is also continuous on 0, 1, because this is just composition of two continuous function on 0, 1. Okay. Now by Oyster's approximation theorem, we can say that what? We can say that there exists a polynomial q that qx minus f of root x, this is less than epsilon by 2. Okay. Now define px equal to qx square plus f of 0 minus q0. See that like that if p of 0 equal to 0 and p dash 0, sorry, p of 0 equal to f of 0, p of 0 equal to f of 0, and p dash 0 equal to 0. Now we have to show that this polynomial p approximate f on 0, 1. So px minus fx, this is less or equal to supremum of px minus fx, supremum of 0, 1. So what is supremum of px minus fx? See, uh, px equal to this. So this is supremum of ux square minus fx plus f of 0 minus q of 0. So this is less or equal to x belongs to this ux square minus fx plus f0 minus q0. We can write this is as root x belongs to 0 1 ux minus f of root x plus f of 0 minus q0. So this is less than epsilon by 2 and this is also less than epsilon by 2. So these f a p approximate f on 0 1 uniformly with these two properties. Okay. So why f of 0 minus q of 0 less than epsilon by 2? This is from a. This is less than epsilon on 0 1. So this is less or equal to f0 minus q0, right? Because 0 belongs to this interval. So this is also less than epsilon. Now we will give you last one. Homework 5. Hmm. Let f 0 1 to r be a continuous function. Then does there exist a sequence of polynomial sequence polynomials such that function Pn equal to f 0 1. Okay. Any questions? I will stop here. All the best. What you will say?